Hello, and welcome to the 9th video in the C++ for Beginners series. In this video, we'll be going over arrays and vectors. These data types allow us to store and work with large amounts of data. So let's begin. Arrays in C++ are used to store multiple values within a single data structure. Up until now, we have been using variables to store a single piece of information at a time. If we want to store 5 numbers, we would need to create 5 variables. If we are working on some type of weather-related program, say to store the daily highs for the past year, we would need 365 variables. I think you can see the need for a better solution. In C++, we have access to arrays and vectors. I'll be covering vectors shortly, but for now, let's focus on arrays. We can store multiple values of the same data type within an array. The number array shown here holds the same data type as the multiple variables shown above. In this case, we're storing integers. The 5 in square brackets represents the amount of data that the array can hold. In this case, we want to store 5 elements of a type integer. We can specify more elements if we need them when we create the array. So arrays are declared in the form of data type, name of the array, square brackets, which we can use to indicate the size of the array. When arrays are created, they use a contiguous span of memory to store data. This is why arrays can only be sized upon declaration. As shown in the example, arrays would store integers in consecutive memory addresses of 4 bytes each, which is the size of an integer. Notice also that arrays are ordered by an index starting with 0 to indicate the first element. We can use the index to access individual elements from the array as shown on the bottom of the slide. This example retrieves the value 42 from the 4th element of the array, which is referenced by index 3. Remember, in computers, counting from 0 is very common, so in this example, element 1 is referenced by using index 0. Element 2 is referenced by using index 1, and so on. Okay, so let's take a look at some example code. I've already written some sample code to help move us along. As you can see, I've created 3 arrays, each holding 5 elements of data. They are for the most part just simply showing different ways we can declare and initialize them. We then access the data by specifying the index of the element we want, as shown here. We're retrieving the value of 42 from index position 3 in the array, which represents the 4th element. Again, indexing starts at 0, so the first element is at index 0. Thus, the 4th element is at index 3. Also note that the last index of an array will be the array size minus 1. So for instance, here we have an array size 5, 1, 2, 3, 4, 5. The last index is actually going to be 4 because we have 0, 1, 2, 3, 4. Okay, so let me compile and run. As you would expect, we retrieved the value 42. Okay, let me bring up another example. First, let me uncomment it. This example shows that, like with variables, we can declare and initialize an array in separate steps. Here we have a new array, array 4, that stores values of the data type double. The first line declares the array and sets the size to 3, or 3 elements. The second line assigns values into the array by referencing their index. Again, we can also access the data by index as shown in the output statement. If we compile and run, we get a value of 33.3. Okay, let me bring up another example of retrieving output from our array. As you can see here, we can use for loops. Loops work great, and as a bonus, since both loops and array indexes start counting with 0, they're easy to work with. Here's a for loop iterating 0 through 5. You can use the iterator variable I to reference the array index. So on the first run through the loop, the iterator is set to 0. It returns the data at index 0, and it prints it to the screen. Then the loop repeats, so it will print out the contents of the entire array. When I compile and run it, here you can see the results. Let me comment out all the above code and move on to the next example. I have two additional examples of using arrays that I placed inside of functions, simply to make the code easier to follow. The first function, myFirstArray, declares and initializes a 10-element array. The next line is the one I want to explain in more detail. While with these simple examples, it is easy to determine the size of an array. In a real program, this might not be as easy. Also, the array size could be changed at some point and break any hard-coded numbers that we may use. Since the size of operator, when used on an array, returns the size of the array in bytes, we can't really use that. Do note, though, that in the latest versions of C++, I believe in C++ 17 and 20, there's an added function for this, but we'll be sticking with this method for now, as it still works fine even if you are using a later version. Getting back to the example, we want to get the number of elements in the array, not the size in bytes. If we use the size of function on a single element, we can obtain the size of just that single element in bytes. Here I'm obtaining the size of element 0 in our array. The size will match the data type. So in this case, since we're using integers, it's going to require 4 bytes per element, so this should return 4. So this line of code is simply taking the size of the entire array, which, because it is 10 elements, would equal 40 total bytes of memory, and dividing that by the size of a single element, or 4 bytes. This result corresponds to the number of elements in the array, just what we need, which in this case is going to be 10, since 40 divided by 4 is obviously 10. The next 3 output statements will just print out what I just explained. Now down in this loop, we can use the value of n, which is set from the division of the array size by the element size, or 10. Remember that the last index in an array will be the number of elements minus 1. So in this example, 9 is the last index position. So just like earlier, this loop will iterate through the array, printing out values from index 0 to the last index, in this case n minus 1, or 9. In earlier videos, we have done similar work with loops, so this should be very familiar to you. Now just to show some things we can do with the information in arrays, we can also use the sort function to display the data in an ordered way. Do note though, if you're going to use the sort function, you will have to include the header algorithm. This last for loop is simply the same as this one up here. It's just used to print the results after the sort. So let me go ahead and compile and run. And here we can see our results. I just put the inside myFirstArray to show that we're indeed using this function. So size of the entire array in bytes, we return 40. Size of a single element in bytes is 4, again because we're using the integer data type. So 40 divided by 4 gives us the size of our array as far as the number of elements. So n is set to 10. Then we use n in our loop so we can print out first the initial order of the elements, and then after sorting, the ascending order of elements. I've now brought up a slide giving a quick overview of the examples I just covered. Here you can see the array example we just used, containing 10 integers. Underneath is the visualization of the array representing how it is stored in memory. Note again that we reference the arrays by their index values as shown across the top. Each data element is represented by a block. Underneath we have an illustration of their memory allocation. In this example I'm just using 1000, but in reality it will be something else. Our array starts at memory location 1000. Notice though that this is in hexadecimal format, not decimal. Also worth mentioning is that both the array itself and the first element are referenced by the starting address of the first element. Since our data type of integer needs 4 bytes for storage, we can then move up 4 addresses in memory to reach the second element at 1004. Also keep in mind, the smallest addressable data unit in a computer is 1 byte, so addresses indicate bytes of data. So this pattern continues until we reach the last element. Then at the bottom, I've shown the array after the sort function has been performed on it. Notice the data elements have been rearranged, but the index and memory addressing stays intact. Only the values have shifted around, but the structure of the array remains the same. We will of course need to use a different index to access a particular value. For instance, value 93 was retrieved using index of 3 before. After the sort, we can now access it using the last element, index 9. Let me go ahead and copy in a snippet. Okay, let me go ahead and compile and run this. Now you notice we've printed out the index, the value in the index, and the address. If you look closely, you can see that all the addresses increment up by 4. Remember, this is hexadecimal, so we're going to use A, B, C, D, E, and F. So going from 8 up 4 is going to give us C, which is equal to the value of 12 in the hexadecimal. And going from C, 12, up to 16, which actually resets to 0, 4, 8, and the pattern repeats. So we can see that each value is actually occupying the memory space 4 bytes from its predecessor. In case you're wondering, we can access the address of an item by simply prefixing it with an ampersand, which has returned the address instead of the value inside it. We'll cover this in much more detail when we get to pointers, but for now I just wanted to point that out. Okay, now let's move on to our last example. Just comment this out. Comment this. Okay, let me go down first and explain the code. So this is very much like our last array, but we declare it and initialize it a bit differently. First, we're creating a constant integer n of type 10. Here we're creating an array again, my array, but this time we're using n, the capital N, for constant as the size. And this time I'm actually using a loop just to insert some random values into the array. I'm not going to cover it much in this video, but rand allows us to generate a pseudo-random number. In this case, it's a range from 100 to 999. If you're interested in the code for this, just look up rand. I'm not going to cover it in this video. Then as before, we just print out the contents of the array. First, we print out the contents before sorting. Then we print out the contents after sorting. In the last example, I'm using the sorts comparison function and feeding it the greater function just to perform a reverse sort. Now if I run the program, I give my output, contents of the array, the original order, contents of the array after sorting, notice they're ascending order, and the contents of the array in descending order. One final note before moving on to vectors. We rerun this code multiple times. You may notice that our random numbers aren't really random. They're random, but they don't change between sessions. It's not a big deal for this example, as I simply wanted to use rand for some numbers. But if you did indeed want to have different values every time you ran the program, we could easily do that. First, in order for this new example to work, we're going to have to add an include, in this case time. Then at the top of the function, you just want to randomly seed a random function with the value of the current time. So again, this isn't truly random, but it will give our program a little bit more random appearance when we run it. So now we go ahead and compile and run it. Notice the values. Let me run it again. 573. 589. So you get a little bit better appearance of random numbers, but again, these aren't truly random. Okay, let's move on to vectors.